Hello from the Forcetronics YouTube channel. Welcome to Reduce Noise in your sensor measurements with an active low-pass filter. And this is part 2 in a 3-part series. If you haven't watched part 1 yet, I recommend you do that before we watch part 2. And by the way, if you saw part 1 and you like it and you like what you see in part 2, please subscribe to my YouTube channel. All right, let's get started with part 2. Here's an overview of the different parts. We did part 1 already. In part 2, we'll be doing the PCB layout for our signal conditioning or filter circuit with amplifier. And just to be clear, we're going to be doing more than just the layout. I actually have the layout done. I'm going to show it to you. But a lot of what we're going to talk about here is some of the considerations you have to worry about when doing a layout when you're working with precision analog circuits and for doing precision measurements, we'll say. And then in part 3, we'll test our circuit, our real circuit. We'll build it up and see how it turns out compared to the simulation. Here's just a reminder of our circuit, our signal conditioning circuit. Here's our sallen-key low-pass filter. We have our 2 resistors, 33K resistors, and our 2 capacitors. Then we have our gain amplifier. And basically, we want to use a gain amplifier so we can make sure the signal uses the full range of the ADC so we can get maximum resolution. Okay, let's talk about some guidelines when we're working with precision analog components or analog signals as well as ADCs. So this is some basically, I'll say, layout guidelines. And one thing you want to make sure is you have a large ground plane. I think a lot of people know this already, but the idea is ground is not ideal. We like to think of things as being ideal. Having a large ground plane helps make sure that your ground and the level of your ground is fairly uniform throughout your design, throughout your circuit that connects to the ground. And then also, big ground planes can also block EMI, electromagnetic interference, so outside noise. So that's why we want to have a large ground plane. Also, you want to keep your analog signals, especially low level signals like the one we're doing here for the current measurement I'm using, the current sensor I should say. We want to keep them away from noisy parts of a design. So this could be switching power supplies or switching DC to DC converters, because those are noisy. If you're using a linear, power supply or converter, that's fine. Those are less noisy. But you still want to keep them away from this design because those components can even get hot. So then they can transfer heat from the ground plane to your circuit, which can then affect its accuracy as well. Then also there's the high-speed digital signals. So think of things like USB or SPI. You don't want to have those pins or traces right next to your analog traces. And then of course, RF signals, if you have some type of, let's say, PCB antenna, you don't want that anywhere near your low-level analog signals. And then also you can make a separate analog ground. That's what they do in boards where you have a lot of things going on, digital, power. You want to keep those analog signals separate, so you make a separate sort of ground plane for them. And then also, if you have a large design, well, I should say, ground loops. Ground loops can be a concern. Typically in smaller designs, they're not a concern. In larger designs, they can be. I would encourage you to look up ground loops on Google if you're not familiar with them. As a summary, like I mentioned, ground is not ideal. So let's say you have a design that has 2 separate PCB boards in it, and each of those PCB boards shares a common ground. Well, let's say you use 2 wires to connect the 2 PCB grounds together. Well, if those wires are in different spots on the board, what can actually happen is you create basically current flow between the grounds. So, like I said, ground is not perfect. So often, if you have 2 separate PCBs, one ground might be at a slightly higher or lower sort of voltage level than the other. And the 2 wires that you have connected them can actually lead to sort of a flow, a current flow, and that can cause a lot of problems or inaccuracies with your analog circuitry. Okay, and the last bullet's real important. Make sure you understand the weakest link in your measurement. And this goes beyond just this analog circuit. This goes beyond how you're using the ADC on the microcontroller. Because what can happen is you can put a lot of effort into optimizing one area that affects accuracy, but you might ignore another that leads to a lot of significant error that just throws out all the work you did. And as an example, a lot of beginners don't realize when you make a measurement with an ADC, it's often, like this is how Arduino works, Arduino will use VCC as the reference voltage. So your ADC needs a reference voltage, and typically it's from ground to VCC. The problem is though, is if you think VCC is 3.3 volts, but let's say the regulator you're using is actually putting out 3.27 volts, that means every measurement you're going to make is going to be 30 millivolts off because you're not working with an accurate reference. Now, there's things you can do to avoid using VCC as the reference. You could use an external accurate voltage reference, or you can use an internal reference. But the point here is you want to make sure you understand the weakest link in your measurement accuracy chain. And I have a great video series, 3 parts, or maybe it's 4 parts actually, maximizing Arduino's ADC resolution accuracy. Now that focuses on the Arduino Uno and the Atmega 328P, but a lot of what I talk about is applicable to any microcontroller. Okay, another thing when you're working with precision analog circuits or any sort of analog components or any important components to your design is you want to look at the data sheet. So op amps are really sensitive to noise and parasitics. And what are parasitics? Well, we like to assume that a wire or a PCB trace is ideal, but really it's not. And so it has some type of resistance, capacitance, and inductance associated with it. Now, most of the time, those values are so low we could ignore them. But for sensitive circuitry, we want to make sure that we reduce them as much as possible. And op amps is one of those things we want to be sure to watch out for. And so it's important to read the data sheet. I know a lot of people who are beginners to electronics often cringe about data sheets, and I understand they can be intimidating, but the more you read them, the more you look up parts, using Google that you don't understand, the more you'll start to learn how to read them, and it's an important skill to have. And I'll be honest, even for me, when I read data sheets, there's often parts or terms that I don't know that I have to look up. Here I picked out a couple quotes from the data sheet just to kind of show you that they do give you a lot of tips on how to design with the device. So I'm using the TLV 314 op amp for this design. So I grabbed a couple examples. There's more in there, but think of the amplifier circuit we have. We're using 2 resistors there. Well, they give you guidelines on choosing the value of resistors. So, if you're trying to do gain, you basically want to have one resistor be the ratio of another, but they don't say what value. Well, here they're basically saying, choose a value in the kilo ohm range. This will reduce the amount of current you use. But guess what? There's more to this. They have a whole paragraph on it, and they also say, but don't pick too high. Because if you pick too high, then the current value of the circuit is so low that it's susceptible to noise. So they say, don't pick a 100 kilo ohm resistor, but pick one more than, let's say, 10 ohms or 100 ohms. And that's what we did here, so we're good there. And then also here they refer to low-level noisy signals, which is exactly what we're working with. They say, if you're using a filter along with this op amp, make sure that the op amp bandwidth is much larger than the filter's bandwidth, and they say 8 to 10 times. Here we don't have to worry because our filter is 500 hertz, which is pretty low bandwidth, and the op amp, the 314, has 3 megahertz bandwidth. So we're fine there, but once again, an example of something you need to keep in mind for your design. Notice that if you don't follow this, they basically talk about a phase shift. I have not really talked about phase. Phase is an issue when you're working with op amps and filters. I'm not concerned about phase shifts, and that basically means you're shifting on the time domain where that sine wave is, or where it is, or where it starts, or where each cycle ends. Think of it that way. Okay, besides just looking at the data sheet for these tips, data sheets often provide layout guidelines for sensitive parts. So let's take a look at the TLV 314's layout guidelines. Okay, here we are. Layout guidelines. And when I say layout guidelines, I'm talking about PCB layout practices. So they want to make sure they give you these tips so you have the best success with the part. And I'm not going to go through all of these. Some of this stuff will be stuff I already covered. But if we go down here a little bit, they're going to show sort of a pseudo layout where they provide some of these tips. This package is a little different from the one we're using. We're using the SOT23 package, but the same idea applies here. Like, for instance, they say, for your components, You want to make sure that they're as close to the device as possible to get rid of parasitics. And I already mentioned that, but here's another way to do it is when you do the PCB, you make sure your resistors and capacitors that are involved with the signal are as close to the op amp as possible. And think about why they'd want that. Well, they want that because it's going to reduce the length of your traces, which is going to lead to less parasitics. They also mention, for your supply lines, put in a bypass capacitor, because having a bypass capacitor is going to take any noise from the power supply and put it to ground. And that way, the noise doesn't get into the op amp and doesn't affect the accuracy of the signal. Also, they mention keep your signal traces away from your power supply traces as far as possible. So that's another thing we're going to want to keep in mind when we do the layout. But once again, don't forget to look at the data sheet, especially if you're working with a sensitive component or analog circuitry, because they're often going to give you some tips that'll help you have a more successful, accurate design. Okay, let's take a look at the Eagle software and our PCB layout. Okay, here's our schematic in Eagle, and once again, I'm assuming you have a basic understanding of Eagle. I'll put these Eagle files on GitHub, and I'll have a link in the description of the video where you can access the GitHub page. Here's the input. I'm using a screw terminal. So if you remember the current sensor from part 1, I'm going to attach the wires into a screw terminal. Here's the input of our filter. Here's our 2 resistors, 33K. Here's our 2 capacitors, 10 nanofarad. Notice that for the power supplies, for an op amp, you have a positive power supply and a negative power supply. You only have to have negative on the power supply, let's say negative 5 volts, if your signal goes negative. Our signal's not going to go negative, so I'm tying the negative input power supply to ground. The positive one I'm going to tie to VCC, and notice I put in a bypass capacitor, 100 nanofarads, just like the data sheet specified. I don't need it on the negative side because I'm tied to ground directly. Here's my amplifier circuit. The resistor in the feedback loop is a variable resistor, so we can adjust our gain. Here's the other resistor, and once again, I tied this to a bypass cap to reduce noise. And then I just have standard pins, or pinholes, I should say, with 0.1 inch or 2.454 millimeter spacing. So that's what will feed to our ADC circuit. Now, I should mention, normally you probably would have this on your main circuit. I'm just for this tutorial and example purposes, I'm having this on a separate small PCB board. Okay, let's look at the actual PCB layout. Okay, here's our layout. You can see it's fairly small. It's about 40 by 22 millimeters. Here's our input. Here's our screw terminal input. Notice I'm using, I should mention this, I'm using 1206 size surface mount components. I like to use that size because they're easier to place by hand, which is what I do. And notice here's one of our resistors. Here's our second resistor. Here's our 10 nanofarad capacitor that's in the feedback loop for our filter. And here's the other one that's tied to ground. Notice that just like in the schematic, the 2 pieces that are close to the op amp, I have them really close to the op amp in the layout, just like the data sheet instructed. Also, I made a bigger trace than the default trace in Eagle, once again, to reduce parasitics. So I could make it even bigger, but I wanted to make it so it fits the pins on the op amp. So once again, I made the traces a little bigger to help reduce those parasitics. Also, I kept the power supply, VCC, this is VCC coming in here, I kept it separate from the main signal pass, once again, to reduce noise from getting on the signal pass, just like it mentioned in the layout tips. Here is my other op amp, the one that's doing the gain. This is actually a surface mount potentiometer resistor, so I can adjust it. And then here is the output right here. Notice that I have these vias all over. So these vias are essentially connecting my 2 ground planes. So if I press the rat's nest, you can see my ground planes fill in. So I have a top and bottom ground plane covering the whole board. And once again, this is important because you want a uniform ground from a potential standpoint, and you also want a nice big ground to block EMI. And then I use these vias all the way around the circuit These vias are tying the two ground layers together, top to bottom. And this further helps to guard against EMI around these analog circuit runs. Okay, well that's the simple layout. In part 3, we're going to build this up and actually test it. Okay, that's it for part 2 of reduced noise in your sensor measurements with an active low pass filter. Next, we'll do part 3. If you have any questions or comments to add to this video, please use the comment section below. If you haven't already, please subscribe to my YouTube channel and also check out the forcetronics.com store. Thank you for watching, and I'll see you back for part 3.